I think they stopped the construction work here, because otherwise, is there a window open? No. No, okay. It was a bit annoying with the sound. Right. So organic matter. As you see, there's lots of it in the water. This was stated, I actually should mention this, Chris Linder, he is a photographer and a scientist, and he joined many of the expeditions or field trips I've been on, and he's excellent in taking photos. So I steal a lot of his photos, and you see his name on some of the images usually. And here he's with a wetsuit floating in front of us. So today I'm going to talk about organic matter, which I already did a couple of times in the previous lectures, but now a bit more focused, I hope. So several points are gonna pass on classification, also ratios and techniques like absorbance or fluorescence that you can use to characterize organic matter. And also a bit in the end about how it's actually decomposing in the water, and it actually could be turned into greenhouse gases such as carbon dioxide or methane. So yeah, I sometimes show this just to, this is the difference between particulates and dissolved. And many people focus on the copy, and not that many people focus on what's in the filter, while it can be as much important as the dissolved fraction. So 0.2 micron, 0.45, 0.7 micron, it depends on what parts of science you're in, but typically it's a filter and then a filtrate. That's this dissolved part. And keeping that distinction in mind, so you have the total, the filtered and unfiltered together, but also the particulate and the dissolved, and also the organic and the inorganic part. Because in many of the papers you will see abbreviations, and this is just to explain this. So you have TOC, POC, DOC, PIC, same for nitrogen and phosphorus. To some extent it's usually just mentioned as total dissolved phosphorus, but the rest is kind of ignored. So be aware, I hope you kind of follow when you see those, and you now know what it means and what it's based on. So that's one way to look at the organic matter, measure it on the bulk level, so include all the carbon or all the nitrogen or all the phosphorus. But you can also look at specific molecules, like alkanes, which are carbon chains of 20 or 30 carbon atoms, and they are very abundant in leaf waxes. So they sit on the surfaces of leaves and they prevent the leaves from drying out. It's a molecule that's very hard to break down, so you can find it in sediments that could be 50, 60, 100,000 years old. So it's something that's on the molecular level on the organic matter, but you can follow that molecule also in your water to say something about the sources, where it's coming from. It's coming from land, but how old is it if you date the age of the anocane? But also other more compositional groups, like lignin is a very complex molecule. We don't really know what it consists of, except from that it's large and it contains certain structures. But also humic acids or fulvic acid or chlorophyll. And then the way to express these two types of analysis is by either just concentrations of milligrams or micromoles or whatnot, but also use ratios to characterize it. And those are not always that relevant on an absolute scale, but really when you compare different environments or compare a stream from the source to the delta area, these ratios could be very important. So the rest of the talk, I'm basically going to talk about organic carbon, because inorganic carbon will come back in lecture 13, and the nutrients, nitrogen and phosphorus, also in another lecture. So DOC, it's studied mostly more than POC, because it is most abundant. If you add all the carbon in rivers up on in the world, you would have a very big DOC component. So it equals all the living plants and trees and biomass, so us and animals on the planet, but also is equivalent to all the carbon that is in the atmosphere of CO2, so it's a lot. And here you see general concentrations in groundwater or up to bogs, so this is really going up. So groundwater, I don't know if you can read it, is close to zero, and major rivers more between 2 and 10 milligrams per liter, and then bogs could be much higher. The maximum I ever measured is 300 milligrams per liter, and basically very dark and very suspended, so there was a lot of particles in it, but when you filter them out, there was still a lot of dissolved matter left in permafrost, little fall streams. So another classification we often use is alloctonous and autochthonous. Do you know what that stands for? Or can you hypothesize based on other often used terms in society?
I thought that alloctonous DOC originates from leaf matter or that animals that fall into the stream.
And autochthonous?
From the algae and other microbial species.
Yes, exactly. That's correct. So this refers more to like the transport it has seen. So autochthonous has been in the water, it's produced in the water, and alloctonous is comes from another place, but is transported into the water. So often from the watershed or from the catchment. And in most systems you have more terrestrial matter in your water than you have plankton or other types of benthic matter, for example. So DOC is important for microbes. It's very small, so microbes like it and they use it as their food source. So they either use it to build their own biomass, or they chew on it and also release it as carbon dioxide. And as a result, there's a lot of dioxide produced by microbes in water from degrading carbon. And we call this supersaturation of CO2 in the water. So how high would a supersaturated stream be? Do you have any idea? What's our, how do you say, boundary for a stream to be supersaturated and what not? If we compare it to the atmosphere.
Should it depend on the volume of the water body?
Now it should be independent, so it's the concentration of CO2. Yeah, maybe I should have rephrased here, supersaturated compared to air. So we know CO2 concentrations in air are now about 400 parts per million. So if it's higher in the river, it's supersaturated with CO2. In 100 years' time, that definition will be different again because it raises. But in graphs like this, where on the left you could see that the increase in DOC in rivers in Quebec in Canada leads to a higher partial pressure from the microatmosphere of CO2. So more dissolved organic carbon in the water, more microbial decomposition of it, and you have more CO2 in your water. Because the atmospheric CO2 level is at 400, so everything above, basically, all those rivers are all the time supersaturated. Which, in other words, basically is the same as on the graph on the right, means that they're always emitting CO2. Because there's more CO2 in the water than in the air, so the net flux is upwards, which is important from a global climate perspective, because we know water is our source of CO2, and we need to take them into account. Just like the coal paper from the second class that was represented that inland waters respire CO2. They are an active active pipe they call it over there. So for POC, a lot of things are similar in how we describe it. So there's also alloctonous POC and autochthonous POC coming from the outside or already produced in the stream. Another distinction that is often used is petrogenic and biospheric. And petrogenic, well, would anybody here know what that could stand for?
Also rocks.
Yeah, yeah. So, like petroleum, also it has a kind of like a very old, coming from rock source, and in this case, yeah, it's basically the very old radiocarbon dead material, mineral in your water. And biospheric is everything that's coming from plants or animals or biologically produced. And it's easier to actually focus on the biological part, but the other fraction is much bigger. So, what's the function of particulate matter? Well, it provides surface area, so bacteria need something to hold on to when they're in the water, and also they get their food source from particles. But it can also be a source of very quickly degrading